morning, students. How are you all?
Morning, ma'am.
Okay. So, do you remember what we have studied in the last session? Let's do a quick revision. Okay.
Okay.
So, the first important point that we have discussed in the last session is the kinetic energy. Average kinetic energy of the particles inside a body is directly proportional to the temperature of the body. Correct? K average kinetic energy of the particles inside the body and absolute temperature of the body. These both are in proportion with each other. Okay. And what is the next important point that we have discussed in the previous session? We talked about specific heat capacity. Alright? So in order to get to specific heat, we need to discuss two important things. One is Q is proportional to M. The amount to be supplied to a body is directly proportional to its mass. We have discussed this. And what is the other point? The amount of heat supplied to a body is directly proportional to the change in the temperature. Delta T is change in the temperature. So the more amount of heat when we supply, the temperature of the body would be increasing rapidly. So the change of the temperature of the body and the amount of heat energy produced or supplied to the body are in proportion with each other. From this relationship, we have deduced Q proportional to M delta T. Alright? From this proportionality, we have derived specific heat capacity. So, using these two relations, we have deduced the specific heat capacity of an object. Right? So, from these two, we can say Q proportional to M delta T. Alright, now remove the proportionality here and place it with the equation. We get a proportionality constant. Q equals S M delta T. Right, here S is the proportionality constant and which we discussed in the previous session. This to be specific heat of a body. Alright. So now let's define specific heat capacity once again and let's proceed with today's session. See, by looking at this equation itself, we can define specific heat capacity, right? How can I do that? Specific heat is the amount of heat energy required to raise the temperature by 1 unit, and this amount of the heat energy is required for 1 gram, right? By 1 unit for 1, or I can say unit. Instead of saying 1 gram or 1 kg or 1 gram, I can say for unit mass of the substance. So by looking at this equation, we can easily define the specific heat, which is the amount of heat required for 1 unit, for unit mass of the substance to raise its temperature by how much? By 1 unit. So specific heat is the amount of heat energy required to raise the temperature by 1 unit for unit mass of the substance. Get it? Now that we have defined the specific heat capacity and also we have the equation, let's look at the units. CGS units. Let's first look at what CGS units would be. The CGS unit for heat is calorie. calorie divided by, per CGS unit for mass is gram, and for temperature it is degrees Celsius. So the CGS unit of specific heat capacity is calorie per gram degree Celsius. Understand? Next, SI unit for the same. SI units for heat is joule. So joule by mass is kg, temperature is Kelvin. So SI units for specific heat is joule per kg Kelvin. J by kg K. You can note this as clear? Okay. Okay. So in the previous session we have discussed that rise in the temperature, right, or the change of the temperature depends on the nature of the substance. If you remember, in the previous session we have taken, oil in a container, and in a small test tube we have taken oil, and at the same time we have taken water in another test tube, and we have heated these samples for same amount of time by providing same amount of heat energy. So even though the conditions provided are same, the oil gets much more heated when compared to water. So this change in the temperature is entirely dependent on the nature of the substance. Correct? Alright. The same way, the specific heat capacity also depends on the nature of the substance. So few substances might have a greater specific heat capacity, and few substances might have a lower specific capacity. Now, what does it mean when specific heat capacity is high? What it means if the value of the specific heat capacity is greater? By looking at this, we can say if this is higher, that means I require greater amount of heat energy to generate a change in the temperature. Okay? Yes? Specific heat is high, means amount of energy required. So this point is clear, right? The specific heat capacity depends on the nature of the substance. That means few substances might have higher specific heat and few might have lower. So it is different for different substances. Now, what does it mean when specific heat capacity is greater? By looking at this, we can say if the specific heat capacity is greater, that means we need more amount of heat energy to produce change in temperature. In other words, to raise the temperature, we need lots of heat energy if the specific heat capacity is high. So I can say that maybe the rate of rise in the temperature is low if the specific heat is high, right? Because if the specific heat is high, for any amount of the temperature change, I have to give more amount of heat energy. And conversely, if the specific heat capacity is low, then I just need to provide the substance with some very less amount of heat energy, and it will give me change in the temperature. Correct? So the rate of the rise in the temperature would be high if specific heat capacity is low. Get it? Understand?
Yeah.
So in a way, the specific heat capacity gives us an idea of how reluctant a substance is to change its temperature. Right? It gives us an idea of reluctance to change temperature. Okay, and I say then if specific heat is high, the substance is highly reluctant to change the temperature because it demands more heat to change the temperature. And if the specific heat is less, then the reluctance of the substance to change the temperature is low. That means it will demand only small amount of heat to change its temperature. Get it? Okay. Moving on. So we said that specific heat is different for different substances. Why? Why is that? Why is it different? To understand this, we need to revisit this concept once again. Average kinetic energy, proportional to absolute temperature of the substance. So now we know that every object has some internal energy. Yes, every object will have lots of particles in it, molecules in it, and due to the movements of these molecules, every body will possess some internal energy. Okay. So what do we mean exactly by internal energy? So every body has linear kinetic energy. The particles of the body will have linear kinetic energy, rotational kinetic energy, vibrational energy, and potential energy. Right? All these energies together, they make up the internal energy of a body. Okay? Now, whenever heat energy is supplied to a body, that heat energy would be shared among all the molecules of the body in various forms. Okay, the amount of heat energy supplied to a body would be shared by all of its particles among various of these forms. Now, this sharing will vary from molecule to molecule. That means the type of molecule to type of molecule, which means it will vary from substance to substance. Alright, so now when we provide with some energy to any object, if maximum amount of that energy is shared or utilized to increase the linear kinetic energy, then this will result in an increase in the temperature. Right? What did I say? So, when we supply heat energy, that would be shared among the particles in various forms. If maximum energy supplied to a body is utilized to increase the linear kinetic energy, this will result in increase of the temperature. So, if less amount of energy is utilized to increase linear kinetic energy, and the rest of the energy is, if the most of the energy is utilized in the other forms, then the temperature rise would be minimum.
Will you please give me some example of linear kinetic energy?
Yeah. So think of it like this: a body. Think of a box of an object, and you put some marbles in it. So the marbles inside the body are like molecules, right? And think of it this way: the marbles would be moving like this. Yes, to and fro. This is the linear motion of the molecules. So this linear movement is called your linear kinetic energy. Okay, and marbles might rotate. Molecules might have this rotation also,
Yes.
right? That would be your rotational kinetic energy. And atomic particles, they vibrate. Molecules have bonds between them, and they keep vibrating. Think of it this way: you hold a box, put some marbles, and try shaking it. Okay, all the molecules or all the particles or the marbles would be moving in random directions, right? They would be moving linearly, they would be rotating, and they would be vibrating. Yes. So that is when they are rotating, that energy is the rotational kinetic energy for the circular movement. Right? And we have vibrational energy because molecules vibrate. Yes? And the marbles, they keep vibrating due to the movement, right, in a box.
Okay.
And due to that, you get vibrational energy. And they possess some amount of potential energy, which is due to the positional energy. Right? Energy possessed by a body due to its position or distance between the particles. One marble to the other marble, there would be some separation, and due to this, some sort of potential energy would be present. Right? So these are the energies. Now, direct correlation with temperature is our kinetic energy, which is linear kinetic energy. Get it? So, if energy is utilized in the form of linear kinetic energy, then we would be observing the change in temperature. So if any substance, if the molecules of any substance are utilizing maximum of the heat energy to change linear kinetic energy, then temperature change would be higher. If the molecules of any substance are utilizing less amount of energy for linear kinetic energy, then the temperature rise would be low. So this sharing of the energy in various forms depends on substance. It is different from substance to substance. It varies. Get it? And that's why specific heat capacity is different for different substances. And hence we say S depends on the nature of the substance. Understand?
Yes.
Now we know S to be Q by M delta T. Right? Or from this Q equals S M delta T. Yeah? Yeah. So if we know specific heat capacity for any substance, then we can estimate the amount of heat energy we need to supply to change its temperature. Correct? If I have a substance, let's say I have a metal cube with me and I need to heat it to some temperature T. Okay? So I can now, if I know the specific heat of that metal cube or of the cube that I am trying to heat, if I know the specific heat, then I can easily estimate the amount of heat energy I require, right, to heat it. I just need to know the specific heat, mass, and how much I intend to change the temperature. So get it now? Okay, moving on. Let's now look at applications of specific heat, or where this concept can be seen. Alright. So you know what? Oceans are called as storehouses of heat or heat storehouses. Why is that? See, water has a greatest specific capacity. The specific capacity for water is high. That means water would be able to take lot of heat without changing its temperature. That's what higher specific heat means, right? Specific heat is high. That means the substance is highly reluctant to change its temperature. Correct? It does not like to change the temperature quickly, even though you supply it with lot of heat energy. So it will simply take that heat energy, but it will not change the temperature because the specific heat is higher. That means greater amount of heat energy for very less change in the temperature produced. So water has a greater specific heat capacity. Now what happens during the daytime when we have sunlight? The ocean water, they absorb lot of heat by maintaining a moderate temperature. Without showing much change in the temperature, ocean water absorb lot of heat. So what happens at the equator? These ocean water will absorb the heat without much change in the temperature, which means the weather near the equator is being controlled by ocean water. It is being moderated by the ocean water. Correct? And that's why we call oceans as heat storehouses. Now what happens to this heat? This heat would be transported away from the equator by the water, right? Away from the equator to the poles. And there also the climate would be moderated by this heat that's been absorbed by ocean water and that's been transported away from the equator. This way ocean water will moderate the weather and climate at the equator and also away from the equator near the poles. Understand? Okay, moving on. Have you ever observed this watermelons? When they are taken out from the refrigerator, for a very, very long period of time, they would be able to retain that coldness. Right? They won't get warm quickly. Why? Because watermelon contains large percentage of water, and water has high specific heat. That means the change in the temperature is not rapid. It has a very slow rate of change of temperature, right? And that's why watermelons they retain coldness for a longer time. And the third one, all of us love this eating samosas, right? So you might have observed this, even though the samosas appear colder on the outside, and we might think that it would be okay to take a bite, but once we bite, what happens? The curry inside, it would be very hot, right? So even though the outer portions appear cold, once we take a bite, the curry inside would be very hot. Why? Because the curry inside samosa, it has ingredients with greater specific heat. That's why temperature change is not rapid. It has slow rate of change of temperature. Right? Get it? Any questions so far?
No, ma'am.
Alright, let's move on. Take a quick recap of whatever we have learned today. Firstly, we talked about specific heat capacity, which is Q by M delta T. We have defined specific heat of any substance, and we understand now that specific heat capacity varies from one substance to the other substance, and this depends on the nature of the substance. What are the units? CGS units are Kelvin per gram degree Celsius. SI units are Joule per kg Kelvin. These are the units of specific heat. And what else have we discussed today? Why is specific heat capacity different? Because the heat energy supplied to any object is shared among the particles in various forms. If the maximum of heat energy is utilized to increase the linear kinetic energy, then there would be an increase in the temperature or a rapid rate of rise of the temperature. If less amount of heat energy is utilized for increasing the linear kinetic energy, then we don't see much change in the temperature. And this sharing varies from one substance to the other substance. That's why specific heat varies from one substance to other substance. Okay. And what else have we discussed? Applications of specific heat capacity, mainly about oceans, how they moderate the weather and climate. Oceans are called as heat storehouses of the planet. Okay? Alright. So, in the next session, we would be discussing about some more interesting concepts, how to determine specific heat of a solid, and how to calculate the specific heat by doing some cool experiments. And also we are going to discuss about mixtures. What happens to temperature when we mix different samples. Thank you.